we can pass to the second speaker, Niccolò Zagli.
Let me see if you can see the presentation, right?
Yeah, okay. So, Niccolò Zagli took the laurea magistrale in Florence in 2017, working with Duccio Fanelli on finite size, quasi-cycle and amplification effect in a stochastic model of neural dynamics. Then he moved in UK, first at the University of Reading for a master by research in mathematics, then at the Imperial College in London for a PhD, where his supervisor were Grigorius Pavliotis and Valerio Lucarini, and the title of his PhD was Response Theory and Critical Phenomena for Noisy Interacting System. And from October of last year, he's at Nordita in Stockholm with a research fellow position, and today he's going to give a talk whose title is Response Theory, Reaction Coordinates, and Critical Phenomena for Noisy Interacting Systems. Please, Niccolò.
Thank you very much for the opportunity. Yes, today I wanted to tell you a bit about one of the projects I'm involved at the moment, and it stems from my PhD project that, as you said, has been developed with Valerio and Greg. The overall goal of the project was to characterize critical phenomena in systems through the lens of response theory. And today I will talk a bit about interacting systems, multi-agent systems, which you can think of as a kinetic or microscopic perspective on the macroscopic and collective behaviors that complex systems usually exhibit. And the applications of these interacting systems are all over the place in science, going from more physics oriented applications like synchronization or dynamical systems of networks, but they've also been applied to less canonical applications like sociology, opinion dynamics, and also finance applications. The systems we have considered so far are what they're called weakly interacting diffusions, and you can think of them as an ensembles of agents, and the dynamics of each agent is specified through a vector field F that in general describes some non-equilibrium dissipative conditions. And we also allow the system, the agents, to be non-identical, meaning that we associate to each agent as a parameter or a set of parameters that are drawn from a specific known distribution. Then the agents are coupled, and theta is the strength of the coupling. They're coupled through this kernel interaction, which describes pairwise interactions between the agents that we take to be antisymmetric. And the coupling structure here is globally interacting systems, which means that there is somewhat simple systems where there is no spatial notion to it. And on top of it, the systems can be affected by noise, and the noise could be possibly multiplicative. And the idea is that we were interested in assess the response of such systems as we perturb them, we perturb their dynamics. We were inspired by this because we were thinking of the question was, how do we detect changes of macroscopic behaviors in general systems? And usually, as we heard before as well, you try to identify an order parameter, which is some kind of collective variable that allows you to achieve complexity reduction, meaning that you describe the very high dimensional system with some 1 or 2 degrees of freedom that can capture the essential dynamics. And then you try, as you change some parameters of the system, you hope to see that this order parameter undergoes a sudden change, a sudden transitions. And in equilibrium physics, you might have some criteria to some physics intuition, or you might use symmetries to define these order parameters. But in less canonical systems or system way out of equilibrium, there is, especially in applications that are not inspired by physics, there is not always a good physics-informed order parameter. And so the idea was, can we understand the onset of critical phenomena through the lens of response theory, which kind of describe exactly this settings that I've described now. A very brief recap of what response theory is. Response theory was firstly introduced to describe situations where there are some perturbations out of an equilibrium state. But the goal of response theory is to describe how this perturbation changed the statistical properties of the system. But then response theory was generalized to more complicated systems, to non-equilibrium systems, and these could be dissipative, and this is the work of Ruel, or stochastic, and this is the work, for example, of Heirer and Maita. The recap is, imagine that you have a system that is described by a stochastic differential equation where you have a drift and you have a noise term, and imagine that we apply a perturbation. The perturbation we take to be of small amplitude, but it's very generic. So it can be phase space dependent and also time dependent. So basically we're driving the system continuously out of equilibrium. Then we are interested in looking at the statistical properties of the system. So we write the Fokker-Planck equation associated to this. And then we ask ourselves, what is the value of some observable phi after we apply the perturbation? And this is, in a linear response approach, this is the unperturbed observable plus a linear correction. And the linear correction depends on time, and in this response theory approach can be evaluated through the use of a Green's function. And more specifically as a time convolution between the time-dependent modulation and the Green's function. And the Green's function is a complex function. Sorry, it's a very complicated function that encodes all the positive and negative feedbacks of the system. And basically it depends on properties of the unperturbed system. And this is the most important thing. It depends on the specific pattern of perturbation, phase space perturbation that you're considering. And also it depends on the observable, but it does not depend on the time modulation. Usually people, rather than looking at time, response in time, people look at response in frequency. And this is a classic result of response theory where one says that the response at frequency omega doesn't have, there is no creation of harmonics. So basically the response of frequency omega is just the input of frequency omega that is modulated by a complex function, complex valued function known as the susceptibility. And the susceptibility has this physical interpretation. Its amplitude is just the amplification factor of the input at that specific frequency, and its argument is a phase factor. And it's been realized that a very insightful approach to response theory is given by what is called Koopman theory. And Koopman theory was introduced to understand statistical properties of generic dynamical systems. And basically the essence of this is that rather than looking at evolution of trajectories in the phase space, and this evolution is non-linear, you look at linear evolution of the observables. So the catch is that rather than looking at something that is finite dimensional but non-linear, you look at something that is linear, but in an infinite space, the space of observables. But nevertheless, this allows you to use the properties of spectral theory of operators, of linear operators, and this leads to a characterization of the susceptibility in terms of the eigenvalues, for example, of this transfer operator. And physically, this means that you can always see there is a somewhat a universal way of understanding susceptibilities, where the susceptibility is if you want, the response is somewhat a continuous response at any frequency, but there are specific resonances corresponding to the eigenvalues, to discrete eigenvalues of this operator, and these resonances described enhanced responses to specific perturbations. And these resonances, the location of the resonances are, as you can see here, are just properties of the unperturbed dynamics, and they do not depend on the observable or the forcing, but the strength, the coefficients of these resonances does. And this was very useful also in understanding how singular phenomena happen. And for example, singularities of the response can be associated to situations where these eigenvalues get smaller and smaller real part. Going back to the system that we are interested in, so this weakly interacting diffusion, one could study the microscopic dynamics of them, but actually one is more often interested in some mesoscopic description of the system. So we look at observables of these systems. And such systems have a very nice feature, meaning that it is in many interesting cases, you can write a closed evolution for mesoscopic observables. And this is due to the fact that that these systems exhibit what is called propagation of molecular chaos, meaning that they have asymptotic statistical independence, meaning that the more and more connected these agents are, the more statistically independent they become. And this is a very mathematical property, somewhat counterintuitive, but it can be seen. It can be seen in nature or in some specific aspects of it. For example, in this study, the authors studied the activity of a very localized groups of neurons that are closely connected together, and they also share common inputs. And they showed that these neurons actually had very surprisingly low statistical correlations between their spike counts. But nevertheless, in a mathematical way, propagation of chaos can be seen in the easiest way, if you want, as this property. So the n particle distribution of the system, as the number of particles goes to infinity, so as you reach the thermodynamic limit, then it factorizes in a product of single particle distribution. And the single particle distribution rho that you see here, they all satisfy what is called a McKean class of equation, depending on the settings that we're considering. And this is a nonlinear, non-local Fokker-Planck equation. It looks very much like a Fokker-Planck equation for a one-particle distribution, but it has a nonlinearity here in the interaction part, in the drift term, where the nonlinearity is given by the fact that the interaction kernel, the pairwise interaction kernel, is convoluted with the probability distribution itself. And also the fact that we considered non-identical agents manifests itself as the fact that there is an integral overall values of this quench disorder distribution. And being a nonlinear and non-local Fokker-Planck equation, this equation supports multiple stationary measures, and there are exchanges of stabilities among them, and these exchanges are usually seen as critical phenomena in the system. The catch, okay, we have a mesoscopic description, valid in the thermodynamic limit, but the catch is this is still an infinite dimensional problem because the drift term of this equation depends on the full probability distribution. So strictly, this is an infinite dimensional problem. But actually, we realized that if you ask this very simple property of the interaction kernel, meaning that we ask that the kernel is separable, so it can be written as a sum of products that depend only on x and only on y, then this interaction part that was infinite dimension can actually be written in terms of a few or at least a finite number of observables, and the observables are the ones associated to the functions A appearing in this decomposition. In a simple case, like for example, when you take linear forces among the agents, so you have something linear here, then it's easy to realize that the functions appearing here are just linear. And so the observable appearing in this description is just what people usually call the magnetization, for example, or at least the first moment, the first empirical moment. So we have a description in terms of some observables. Are these observables somewhat good? Are they optimal in some sense? And the answer is yes, if you look at them in a linear response approach, because, and I hope to show that they carry a lot of information regarding the system. So they carry correlation, memory, and resilience properties of the system to perturbations. And more interestingly, they actually characterize the development of critical behaviors of the system. So imagine that we have this thermodynamic limit of agents and we perturb it with the perturbation, like I said before, and we observe the response of one of these observables that we have identified. And here's the result. The response of the observable is more complicated than what we saw before, and it can be divided in two parts. The first part, that is mediated by this Green's function G, can be associated to the response of a single mean field agent with respect to the perturbation. And this depends on the type of perturbation that we apply, and it can be associated then to exogenous processes. But then the interesting part is the part that is related to the coupling among the agents, where theta is the coupling strength. And this part is mediated by another type of Green functions that we call Yij. And these Green functions do not depend on the forcing, nor on they do not depend on the forcing, and they can be associated to some endogenous processes that are happening in the system. And as you can see here, this part of the response depends on all the other collective variables of the system. And so we see that there is somewhat a memory effect that is due to the coupling, because the response at time t depend on all the values of the other observables at previous time as well. It's easier to disentangle the response of the system if we look at the frequency space, and we see that the response of these observables at frequency omega are modulated by the susceptibility of the system, and the susceptibility of the system can be written as the susceptibility of a single agent, mean field agent, but it's also modulated, it's also amplified, if you want, by a matrix P that is related to endogenous processes. And in a schematic way, this can be seen as a linear system with feedback. So you have an input, the input is modulated by a single mean field agent, but then it's also, there is a feedback loop due to the coupling among the agents. And the total response is given by the total system of response here. These two formulas, they actually describe the response at any given frequency of the system. And one is usually interested in a smooth regime of the response, where the susceptibility, as we saw before, is a complex valued function with some resonances. Otherwise, one is usually more interested in a critical regime of the susceptibility, where the susceptibility develops some singularities. And the singularities for some real values of the frequency, where there is at that value a breakdown of the response. And from this formula, one can see that the singularity can come either from this part of the susceptibility, meaning that you perturb the system and the mean field agents basically break down. So the modulation of the driving resonate with some resonance, highly resonant spike in the single mean field agent susceptibility, or the singularity of the total susceptibility can come from this matrix P. And this is not associated to the breakdown of every single agent, but basically it means that the response of each agent is smooth, but then the coupling among the agents amplifies the response and makes the system acquire some singularity. In both cases, the signature of the criticality is that the susceptibility can be written as, in the simplest setting, as something that has a simple pole, and the location of the pole depends only on the unperturbed system, but the strength, if you want, of this divergence depends on the observable that we have considered and on the pattern of forcing, on the phase-space pattern of forcing. And I want to show you how this criticality develops in a linear response approach in the probably most well-studied example of phase transitions, which is the Kuramoto model. And the Kuramoto model, in this case, describes a synchronization between phase oscillators, where we have an ensemble of oscillators, each oscillating with their own frequency that is distributed according to some measure mu. But then there is also some nonlinear coupling that tries to synchronize them. And also we have noise.
Niccolò, hai 5 minuti.
Oh, thanks. Grazie. And this interaction kernel is separable, and we can identify the collective variables that I described before. And we know that there is, this system describes an incoherent state where there is asynchrony, but then there is a path, a synchronization transition to a state where there is synchrony. And the idea here is, imagine that we are in a non-synchronous state, and we want to understand, one, whether we are in a critical state, and two, can we characterize the critical onset of this criticality, especially in a linear response approach, so how the system responds to perturbations. And what we propose that could be useful to understand how the onset of criticality develops is to perform somewhat a spectroscopy of a phase transition. So we apply to the system some kind of perturbation, and the perturbation is broad range in a broad range frequency, and then you monitor basically the susceptibility. You evaluate the susceptibility, and in non-critical setting, which are the black lines, you can see that the susceptibility is a smooth function, somewhat dull, because the Kuramoto model doesn't have the resonances due to complicated dynamics. But then at a critical setting, which are the red lines, we see some singular behavior developing. And the singular behavior, of course, becomes more and more prominent as the thermodynamic limit is reached. And this critical setting can be written as a singularity of the susceptibility that has been modified. And in particular, here we see that the system is highly dependent to perturbations, highly sensitive to perturbations at slow frequencies, but quite insensitive to big frequency perturbations. And so, as I was saying, the singular behavior can be written as a modification of the pole, where the pole in omega equal to 0 has been slightly shifted with an imaginary part, and the imaginary part becomes smaller and smaller as the thermodynamic limit is reached. But this way also allows you to identify the residue of the resonance, which kind of tells you the strength of the resonance. And it tells you also how the response is shaped. And it's easy to realize that in this simple setting, the residue has to be imaginary. And if it is imaginary, we have this, just by taking the thermodynamic limit of this expression, we see that the residue can be is estimated by the imaginary part of the susceptibility that behaves like a Cauchy distribution. So it can be read from here. In this case, it's 1/2, and one can actually show in this system that the residue depends on some microscopic properties of the system, and in this specific case, with the integrated autocorrelation time of a single mean field agent. This setting was for a symmetric unimodal distribution of frequency, but oh, sorry, let me remove this. More interestingly, if you have a bimodal distribution of frequency, by doing the same kind of experiment, you can see that in critical setting, there is a pole that is non-zero that arises in the susceptibility, exactly in the same way as before. And in this case, we can see that this resonance is actually non-symmetric, and this is due to the fact that the residue is no longer purely imaginary, and this actually shapes the response of the system in a way. So basically, going back here, this tells you that if you drive this frequency, if you drive the system at a critical frequency, you develop somewhat a phase shift that is due to this real part of the residue. So I have other numerical systems, but actually I want to jump to the conclusions. And I just want to say that, yes, what we have investigated the onset of collective behaviors of mean field interacting systems of this type, where F could actually be described non-equilibrium settings. From the microscopic interaction structure among the agents, we have identified some collective variables, and we have associated a susceptibility of these collective variables that describe completely the response of the system at any frequency. And then we saw that phase transitions arise as singular behaviors, so singularities of this matrix P, the inverse of P. And in finite systems, they can be traced back as a modified version of the thermodynamic counterpart, where the location of the pole is somewhat universal, but the residue depends on microscopic properties of the system. And of course, what I would like to do is to characterize more complex systems where we have a network topology, and there are some ways to do this. And also, I would be very much interested in understanding how singular behaviors of these susceptibilities of the response of the systems arise in more complicated settings where the dynamics of the agents exhibit some resonances. And with this, I thank you, and thank you very much.
Thank you, Niccolò. Thank you very much. So, questions, comments? Stefano?
Hi, Niccolò. Ciao, Niccolò. Stefano Leppi da Firenze.
Yes.
Just to see if I understood correctly what this Metin Vlasov is. It reminds me a bit when you're doing the difference between Lagrangian and Eulerian approach, you know? So in one case, you solve the trajectories. In the other one, you somehow look at all the particles that are in a given volume.
Yes,
in
exactly.
the sense that the deterministic part should be the kind of hydrodynamics term that appear in this context,
exactly.
Right? Is it correct?
Exactly.
Yeah.
Yes. So basically, it can be seen as a law of large numbers for the empirical measure. Exactly what you said. You look at an ensemble of particles that are in. You ask yourself, what is the proportion of particles that are in a specific phase space region, and then you basically find an evolution equation for the thermodynamic limit of this empirical measure.
So in a sense, you go from a set of n Langevin equation to a stochastic PDE for the density.
Exactly. So this is so the stochastic PDEs for the density would be what is called the Dean equation.
Exactly. No, I had just in mind this Dean approach which allows you
to. So basically, the Dean equation it's somewhat takes into account the finite size effect. Yeah. And in fact, there is, but it's all the validity of this equation is very debated. Especially, it's known that that equation doesn't really describe critical fluctuations. Because, of course, the scaling wouldn't be like with the square root of n in a critical setting. But it has been used to study large deviations. Like, for example, if you have a bistable system, then that one describes the statistics of transitions between the two states for the empirical measure.
So conceptually, the McKean-Vlasov equation would be the Fokker-Planck equation associated with this stochastic PDE.
It would be the thermodynamic limit of that PDE.
Okay.
It would be like the Dean equation would be exactly this one plus one term here that describes the finite size fluctuations. This is the law of large number for the empirical measure. So you don't take into account, this is purely thermodynamic, so you don't take into account the finite size effects. And then you can say that in most cases, if you're away from a phase transition, the empirical measure has some fluctuations of order 1 over square root of n around this solution. But then, of course, at the phase transition, what you observe is here, this factor here. The dependence of n is basically the critical slowing down of the system. So you need to take into account finite size effects here. Okay. And this is why you see like this dependence. The system has not reached the thermodynamic limit.
Okay. Thank you. Grazie, Niccolò.
Okay, are there other questions, comments? Okay, if not, let's thank again both speakers of today, Raphael and Niccolò, and see you in the month of July for the last couple of seminars before summer. Grazie a tutti.
Thank you.
Grazie Riccardo.
Ciao, ciao.
Ciao a tutti.